Oh, okay. uh, yeah, please give me the countdown. Okay. Hello, everyone. I'm Suhas Pai, NLP stream owner at ACE, and I'm glad to welcome you all to another ACE Spotlight session. Today's session will be on interpretability and explainability in NLP. We are very excited to have Yuval Pinter from Georgia Tech as a guest today. Yuval will be speaking about his two recent papers, one from EMNLP 2019 called Attention is Not Explanation, and one from Black Box NLP 2019 called Characterize, Seeing Language Through Character Level Daggers. At the end of the talk, he will also be providing a few details about Black Box NLP, which is a workshop that he is co-organizing at EMNLP 2020. Please feel free to ask questions in the live chat. We'll try our best to get it answered during or at the end of the session. And I just have to put this out there. Yuval has done a lot of research on word embeddings, and for people interested in that topic, I highly encourage you to read his earlier paper, Mimicking Word Embeddings Using Subword RNNs. But back to today's topic, and over to Yuval, who will briefly introduce himself and then start with the presentation. Hi, Yuval.
Hi. Thank you so much, Suhas, for this invitation. Thank you, Ace, for hosting me. I'm Yuval Pinter. I'm a PhD student at the Georgia Institute of Technology, the School of Interactive Computing. I'm also a Bloomberg PhD Data Science Research Fellow for this year. And I will, as Suhas said, will be presenting two papers about the general notion of interpretability and explainability in NLP, which is often called black boxes. And I will explain this very shortly. So I'll present these two papers, preceded by a brief intro. So let's skip right into the main problem, the main motivation for why this research into interpretability has been surging over the last few years, especially in NLP, but also in machine learning as a whole. NLP started with this rule-based approach where we develop systems that have very specific rules that we describe, that we define, and we tell them how to decide, and then figuring out how why the machine decided this thing or another is very, very clear. We have the exact flowchart at our disposal. Then about 20 years ago, we started this machine learning, maybe first or second wave of research, where we started defining a bunch of features to prediction or annotation systems, and they weighted them in some way or fed them into SVMs or logistic regression models or other similar techniques. And we still had a knowledge of what types of features are existing in the model and how it's providing a general representation of what it's getting in, and so why it's deciding what it's deciding. Over the last few years, our fields have been overrun by what's called deep learning, where even feature engineering has been taken out of our hands and into the model itself. And at this point in time, all we know about what made a model make its prediction is basically nothing at all. Our only liberty as to how we present our models in the conferences. And so our main question is, how can we find out why or how the models are making its decisions, which also ties to maybe a more intrinsic motivation of when can we trust our models? And this is based on knowing why they make their decisions. So on a slightly lower level, a few reasons we may want to explain or interpret our models. The first is, as I said, to know for ourselves. We want, as machine learning practitioners, to keep developing models. We want to develop better models. We want to know why our previous model failed or what it did wrong that we can now improve. We want to just be able to debug from a task perspective what our models do. More crucially, sometimes models are just one phase within a pipeline. So a model's prediction, for example, in the medical domain, can then go to a physician who then needs to be assisted by the model to make some sort of diagnosis or maybe a prescription. Or another example is that of the judicial system, where Sometimes judges make decisions also assisted by a computer algorithm. And in this case, it is, of course, very helpful to let them know based on what information they made their prediction that will now need to be adjudicated. Another topic is bias, which is also a rising field of study in machine learning at large. If a model is provably treating, for example, different demographics, the demographic users in a different way, or predicts different things for different kinds of groups, then knowing why models make their predictions can also help us identify the sources of these bias and maybe mitigate them, or advance research into systems where if we can't control the bias, at least we can know where it's coming from. And lastly, sometimes it's just a legal requirement. So in some jurisdictions, it is not permissible to deploy machine learning methods if you cannot explain per instance why the machine made its decision. So one example is some financial sector applications where if you give someone their credit rating, you also need to give the reasons for that credit rating. A second thing I wanted to address before we dive into the papers is terminology. So this field is relatively new and thus is very amenable to our personal interpretations. So this is a recent thread from Jan LeCun, which I do not agree with, where he says there is no completely accurate intuitive explanation of why airplanes fly. But maybe one could argue that a more accurate correlate to machine learning interpretability is an explanation of why an airplane flew in one direction and not in another, or why it flew in a particular altitude or so. And this is exactly the point that I'm trying to make, that you can define explainability or explanation towards a direction that would then make your goal easier. If you want to say that it's not important, then you can just say that it's this thing. And if you want to say that it is important, then you can try and make it into a stricter definition. And you would be just as persuasive as maybe this series of tweets here. Other terms that are very loaded and not. Oh, sorry. This is a attempt by Zach Lipton to address these terminology issues. Two papers about the mythos of interpretability. I recommend reading these papers. Other terms that are in this kind of haze are interpretability, as I mentioned, explainability, transparency. What does it mean for a model to be transparent? What does it mean for a model to be faithful, even if it is explanation? I will be using these terms, but I want you to remember as I use them that I am using them basically to my best understanding, to the way that I would like to see them applied. So I'll just read this out. We'll talk about this throughout this session, but the more I read about this topic and the more I give this talk and the more I think about these issues, I become more and more convinced that there isn't a definition for these notions right now that we can impose on the community and everybody will be satisfied. These things carry too much intuition. So with this in mind, I'll be presenting these two papers. One of them is more related to interpretation, by which I will be taking one neural model and some first principles approach, try to figure out how this model is learning its task and whether it differs as the conditions change. This is the character eyes paper. And then something more related to explanation. So based on a previous paper which claimed that certain methods cannot be used to faithfully explain a neural model, namely attention, what have they really shown, and can we do this in a slightly different set of assumptions? And that is, attention is not explanation. So starting with character level taggers and how they can see language. This is work with Mark Marone from our lab and Jacob Eisenstein, who is my advisor at Georgia Tech from Black Box NLP last year. So I hope most people know what taggers are. They take a sequence of words in any language, and the task is to output this series of tags, in this case part of speech tags, and their morphological attributes. So the as a determiner, walked is a verb in the past tense form, etc. A neural tagger performs this task by running some kind of neural method in the middle. It could be an LSTM, it could be a CNN, it could be a transformer. Today, it doesn't really matter as long as it's a neural method. A character level neural tagger does this task by first decomposing the words in the word level input into their specific characters. They do this by adding another layer beneath the word level and then attaching them to some kind of word representation on the higher layer. And a character level recurrent neural tagger, which will be our focus for this presentation, represent the words from their character level based on an RNN, so a recurrent network that goes along the characters within a word. So the first question that we asked here is, can the success in detecting certain kinds of parts of speech or of morphological tags be explained by them finding morphemes? So morphemes in English, for example, is this ed, which denotes a past tense verb. And our claim is that, our hypothesis is that maybe if a model can detect this ed sequence of letters, then it somehow signals or attaches it to this prediction for a past tense verb. This phenomenon where one sequence of contiguous letters is exactly correlative with one type of morphological attribute is called agglutination. So this is, an agglutinative language does this a lot. Other languages may have the same type of agglutination, but from the other side of the word. So ed is a suffix, but maybe another language also adds the in front of the cat for a single token, and then this is called prefixing morphology. There aren't a lot of languages that are high resource to do this, but Coptic is one of them that has resources at all. What about discontinuity? So certain languages have this property where the morphological attributes are not corresponding to a contiguous span of characters, but the characters are sort of interspersed within the words. Some of these languages are Hebrew and Arabic. This is called introflexion. And so using these properties as an example for how languages correspond character sequences and morphological attributes, we were thinking of connecting this with the idea of a character RNN by, from one hand, seeing how models encode these different linguistic patterns, this agglutination, this prefixation, and this introflexion. And on the other hand, try to find how languages are based, how different languages, what the properties of different languages are based on how the models perform on them. Okay. So when I said that we're doing this from first principles, what we started from was the basic unit within the hidden layer of the RNN. So these are layers that are usually, they use 128 hidden states, for example, and each of these units or neurons is known to, or we hope to find that it is able to detect a certain pattern within a language. So if indeed these things are true, then we would expect that since this is a sequential model, it will work better for agglutinations, right? Because there's a certain suffix or a sequence of characters that correspond to a certain type of prediction. It would be difficult for interreflections because that is interrupted. The morpheme representation is interrupted within the word. And also that if there's any effect for the directionality of the unit within the hidden state layer, then that would look differently whether the language is heavy in prefixes or suffixes. And so this is going to be a multilingual typological survey of this type of correspondence. So just to show you one short example, a language like Turkish is highly agglutinative. Each part of this final word here, evlerinizden, I hope I pronounced that even close to correctly, corresponds to a very specific morphological attribute. So ev, ler, inis, and then are each very demarcated morphemes within the word. And then when we run a character RNN to predict part-of-speech tagging and see the activations on it, so this is one unit, unit number 3, and we see that it activates, by which we mean the state value changes a lot between these two morphemes and between between the first two morphemes and between the last two morphemes. So there is some evidence that there is some detection going on at this level. Same can be said for this other unit, which is a backward-facing unit. So also you see these jumps between the fourth and the third morpheme in this case, and the second and the first, because it's going from the N to the E. Before I go to the actual interpretation technique, our model and data are taken from universal dependencies. So universal dependencies has almost 100 languages today that are annotated, among other things, for part-of-speech tags and morphosyntactic descriptions. The reason that we took 24 was that we wanted to keep this linguistically diverse as possible. The vast majority of languages in UD, universal dependencies, are not agglutinative or introflexive. So we took as many as we could from these classes. Also, affixation is very heavily skewed towards suffixing languages like English or most European languages. And the single, and we just took here every single non-suffixing language into our data set. So that's 1 prefixing languages, 2 that are non-affixing at all, and 2 that are equally prefixing and suffixing. This is data based on walls. So this is the full list of languages. I won't go into that, of course. Our model was a simple bidirectional LSTM and then an MLP to predict the tags. We did our best to keep as much of the actual modeling within the character level. That was a very important part, so that we can try to isolate our parameters as best as possible. And so we did not use any word embeddings. The only representations for the word level are coming from the character sequence. Surprisingly enough, if you jam enough hidden units or embedding size into the character level, you actually don't lose a lot in terms of prediction accuracy. So the accuracy of our models is near state of the art, even though there is no word embedding level. And we just use 256 character embedding size. So now for the method itself. What we did was training the model on all of the training data words, and then we collected all of the activations for all of the units from all data words in all languages. So again, we have these maps that show how the activation works for a given unit on a given word. And then we aggregated this one image based on the average activation, the average absolute activation. So in this case, 0.42 for this word. And then we took all of the words in the data set for a given hidden unit and created this table of contingency for it. So on the column side, we have the bins of the activations for this measure, for this average absolute for each word, and then we bin that against what true part of speech each word is. So our hope is that if this unit can tell apart nouns from other words, it will bin all the nouns in the same area of the activation metric. And so what we can compute to kind of turn that hypothesis into a number is the mutual information. So we call this the part of speech discrimination index, or the PDI, where a higher PDI would correspond to a hidden unit that is better at discriminating units, discriminating parts of speech within this language. Okay. So now we have a single number, this PDI, for one hidden unit in one data set in one language. And then we collect all of these and plot them from largest to smallest, and see and then aggregate them into 2 metrics that are now language specific. So for an entire language, the sum of all of these MI scores is going to be the area below this this whole curve. That is going to be the total mass, what we call, which should correspond to how easily the character RNN in this language was able to tell parts of speech apart based on character activations, and also the percentage of forward units that are before the mass median. So this is for this directionality question, if prefixing languages correspond to forward-facing units or the other way around. So just to look at two languages for this metric, we see that Coptic, which is an agglutinative prefixing language, is on one hand very high in PDI compared to English. So allegedly, the units are more easily finding the morphemes and aligning them with the morphological attributes. And a lot of the heavier units are forward-facing. This is the blue colored units. So maybe they find the prefix and then they remain at an activation level that is indicative of the part of their speech. On the other side, we have English, which is a fusional suffixing language, and we see the exact opposite pattern. So a relatively small mass of the total for all of its units, and the most informative units are backward facing. So allegedly, they find the suffixes and then they remain at the good activation state. When we turn to the overall numbers, we see that the agglutinative languages are indeed clustered at the top of the total PDI mass metric. And on the other hand, we have the interflexive languages, which we hypothesized would be more difficultly part of speech discriminative at the very bottom of the table. Although I do have to note one confound is that both Arabic and Hebrew and the other two languages in the bottom of this table are using non-Latin character sets. We did not perform a second evaluation to see whether that is somehow a confounding factor for this number. We also performed a different study that is more empirical. I'll just gloss over this TLDR just because I think the setting is unique enough. We looked at the performance of both the bidirectional models, where an even number of hidden units are forwards facing and backwards facing, versus ones that are unidirectional, which are only forward facing or only backward facing, and those that are kind of in the middle. So most of the units are forward facing, but some are also backwards. We call these sesquidirectionals. Unfortunately, we didn't find any conclusive evidence. So some languages actually did better in the completely unidirectional setting. So that is an interesting thing to look into if you're designing taggers for agglutinative languages, especially. But we couldn't find anything that suggests a sweet spot somewhere in the middle between a completely unidirectional and a completely bidirectional model. Okay, so this was the first paper. If anybody has any questions about that study, I will be happy to hear them now. Give me just 1 second. Excuse me. Okay, so we'll move on. The second paper is Attention is Not Explanation. It is from EMLP 2019, performed with a member of our lab, Sarah Vigreff. And yeah, so let's start. So this study is focused on a different type of model. This is classification models that start from a sequence of words. So if you have this very simple IMDb review, the movie was good. We want our model to predict that it is positive, that it is a positive review. And if we run a neural classification model through the words and onto the prediction score, specifically recurrent models that are, for example, LSTMs, and add an attention layer that weighs each word from the input, or each hidden state from the blue layer to make the prediction, then we end up with what are called attention maps. So these are basically dictionaries that go from the words in the input to the attention score that was assigned to them from the attention module. And they're very often used as a source of explanation. So you can see them, the heat maps imposed on the words in some instance to excuse me, to try and explain what words the model thought was contributing to the prediction. And it has also evolved to a state where we start seeing works where people extract these as gold truths, and later, for example, extract lexicons that are supposed to correspond with given prediction labels. So now we turn back to my my introduction of what explanation is. So this one paper from NACL, Attention is Not Explanation, by Jane and Wallace, proposed that a faithful explanation for an attention model needs to be exclusive. So in this case, if we deliberately change the attention maps from focusing on movie and good to focusing on the other words in the instance, and the prediction does not change to negative, then we're in a problem, because the initial explanation given by the model was not exclusive. Okay, so if we change the attention maps enough, we need to get to a different prediction. Another work from the recent year, from ACL 2019, is Attention Interpretable, from Serrano and Smith, and their claim, or at least their experiments try to show that a faithful explanation needs to be robust, which means that if we remove words that have low attention scores, the prediction shouldn't change. And conversely, if we remove words that are very highly attended by the model, then the prediction should change at some point, at least, or if not very fast. And they tried to do that, and they showed that it's not very easy to do for some of their for the models that they examined. We're going to focus on the first of those assumptions, and we are adding our claims to this. So in our paper, we say that attention as a faithful explanation needs to follow a few different desiderata. So firstly, it needs to be a necessary component for a good performance of the model that we are claiming it explains. So it can't just be an add-on that if you can remove, you can still use it to explain. It needs to be part of the actual model that is being explained. Our second claim is that in order to achieve an adversarial distribution that predicts the same prediction, it needs to be consistent across the entire data set. So we need to be a trained model that can vary attention distributions while giving similar predictions. And lastly, that attention weights should work well in uncontextualized settings. So if you can achieve, if a model can learn attention weights that are then usable in a brand new model that did not have all of the underlying framework, then it might still be a useful explanation. And I'll get to and each of these we now check empirically and see how they can be used or not be used for model explainability. So for the first experiment, we reran the Jane Wallace experiments on 6 data sets, and just removed the attention module from the model. So this is the basic setup, right? We have this attention layer that gives the weights onto before the prediction, and we compare that to a model where there is no attention at all, and everything is just set to uniform. So all tokens, all inputs are attended to equally. And these are the data sets that we use. So two medical prediction tasks, diabetes and anemia, both um, uh, for predicting whether a patient has a certain condition based on the clinical note given to it from the physician. Two of these, IMDb and Stanford Sentiment Tree Bank, where we need to decide whether a review is good or bad. And two news data sets where the prediction task is for a specific genre. So is this a sports article or a financial or one of those? So we ran this experiment on all these 6 data sets, and we found that not for all of them attention is actually useful. So look at these 2 news data sets. They are very close in performance to their uniform counterparts. And so we only continue to use these 4 data sets from where attention actually makes a difference. For SST, it's kind of on the borderline, and you need to keep that in mind because this will also show in the experiments. That SST is more of an edge case here. Okay, so our next task was to search for the adversarial models. So we're claiming that if trained models can vary in attention distributions while giving similar predictions, then that means explanation might not be extracted from the attention weights themselves. So how do we measure these two variables? First, we use total variation distance for the prediction accuracy. So if we have these 2 models, one of them is the stars, one of them is the diamonds, and they each make these different predictions for each instance, we compute the TVD as the sum of these red bars connecting each prediction in each model. And so we want this to be as small as possible for our experiment, while the second metric, which is the Jensen-Shannon divergence between the attention distributions, to be as large as possible. This is not as easy to show graphically, but broadly speaking, what JST looks at is cases where the ratio between the distributions for a given word in the instance is very large. So where the ratio is large, that would contribute towards a large Jensen-Shannon divergence. The way we experiment in this part is by an explicit experimental setup. So we train an explicit adversarial model where both the attention weights and the prediction are known to it, and it attempts to keep the same prediction while staying as far apart from the weights as possible. So there's this TVD term that is the main loss objective, and this KL term that is larger as the attentions are farther away from the original ones, and this lambda parameter that allows us to pick between more accurate predictions and more divergent distributions. We compare this with a random seed variance test. So we just run the same base models just on different random seeds, just to see what we expect in terms of variance from attention weight. So these are not adversarials, but they are plausible baselines for what we expect divergence to look like, because this is not something that we have a clear intuition about. We also compare against Jane and Wallace, whose experiments were basically the same end goal, but they did not train an adversarial model. So they took each instance's prediction and attention distribution on its own, and just tried to fit a different attention distribution to predict the same prediction, which we argue is not consistent for this term, because it's not consistent across the data set, but rather per instance. Okay. And I'll be marking these, the random seeds, with these triangles, and the Jayden-Wallace results with this cross. And so the plots will look like this. On the x-axis, we'll have the attention divergence. On the y-axis, we'll have the prediction difference in TVD. And our goal, or a goal to prove that attention is not explanation, would be if a model can easily reach this lower low corner, the bottom right corner, meaning that it can we can achieve a very similar prediction with a very different attention model. And the interesting area that we will focus on will be everything on the right of the random seeds, because that's basically our baseline for divergence on a given data set. So we'll start with the diabetes data set, which we felt was the harder one. Again, remember that from the first experiment, it was indeed shown that attention is very helpful there. So we see that Jayden-Wallace, their non-parametric approach does reach that bottom right corner, but for us, which are these purple dots on the line for different lambdas, it is actually very hard to get to that area. So if we focus on everything to the right of the random seeds, it even looks harder. So if you want to achieve a good divergence, then you pay dearly with your prediction difference. So it's not as easy to make adversarial attentions on this data set. And we would argue that this data set is one where leaning on attention weights as explanation is not implausible. So it's relatively okay, as opposed to the Stanford sentiment tree bank, where our experiments show that it's very, very easy to achieve more attention divergence while barely paying for it in prediction difference. So for SST, we would recommend not to use attention weights as any motivation for prediction making. Just for some examples, so this is an example from the IMDb dataset, Brilliant and Moving Performances by Tom and Peter Finch. This is the entire instance. The base model, for some reason, attends to and to Finch. I agree that it's not a very good, not a plausibly sounding rationale. But the point is that the Jayden-Wallace method finds that if you only attend to the word performances, you can achieve a similar prediction. Whereas in our model, it is much harder to actually go very far from the same attention weights if you have the same scores for each word contributing to the outcome. Onto the final setup. We think that this is a more extrinsic way to provide motivation or intuition for explainability of attention. And this is where we pit our attention distributions to an uncontextualized setting. So what this means is now we change our underlying model to just a bag of words. So each word is disconnected from the words, from the other tokens in the instance. It is just an MLP for each word in itself. And there is some layer for weighing the scores given from each word before making the prediction. So we change this layer to be either a uniform weights untrained, or the second column will be for weights that are trained together with these with the weights in the MLP, or we just change them to the attention weights learned in the base attention LSTM plus attention setup, but are not retrained. So these are going to be just frozen weights, but given from the attention layer of the LSTM trained one, from the contextualized setting, basically. So we would argue here that if we can achieve high performance from just the attention scores, then we can say that these the weights that were trained on the LSTM actually did capture some relationship between the inputs and outputs, because one claim that was made against using attention weights to begin with was that LSTM states can hold information about the entire context of the whole sentence. That's what LSTM is for, basically. So we're using this setup to try and tease that part out. And I think that we showed this. So you see here the scores for the uniform weights and for the trained feed forward weights, and they are all surpassed by our attention scores that are taken from the base, from the LSTM base. So even outperforming a trained multi-layer perceptron is, I think, a convincing proof that that attention weights have merit, at least in most of these setups. And again, SST is an outlier where the improvement is marginal. So in conclusion, we presented these three ideas of what we think are a faithful explanation. These three methods, which we recommend for practitioners from now on to at least use some of them before they make claims about their prediction and the explainability of their attention mechanisms. And also, we showed that given that this is all very dependent on what task you choose or what task you have, and so we again implore researchers to consider these methods for motivating their explanation on these methods. So this is it for attention is not an explanation. I have a short concluding section. So let's leave questions for after this. One study that is under submission for ACL, and so I can't go into too many details, is a collaboration between Sarthak Jain, Byron Wallace, Sarah Vigraf, and myself. And we are trying to take another look at this explanation and faithfulness by creating a model that is immune to all these criticisms. And by that I mean that if so far we used the interstates from all that were already trained, or we removed inputs in the case of Serrano and Smith that were already seen by the models that were trained on this form, now we will try something that's more surgical. So we train a first model. This is the purple cloud that makes the predictions and provides the scores. A second module that is independent from it takes these scores and uses them to delete some of the words from the inputs. It creates a brand new input that is an ablated version of the same data set. And then a brand new model tries to predict, to make a proper prediction of the same label from the initial task. And this is a way to show that since the scores or the attention weights or whatever weights there are were given by the first model, then as this second model does better, it is more of a signal that those scores were good, and ergo that model was better. And last but not least, as Suhas promised, this is a call for people who want to contribute to the next iteration of Black Box NLP taking place in Punta Cana, Dominican Republic. This will be in November 11th or 12th, and the submission deadline is on July 15th. We welcome all work on interpretability, explainability, and everything related to what you heard right now. There will also be for the first time this year, will also include a shared analysis mission. It's not exactly a shared task, but it is going to be a way for many groups, we hope, to contribute an analysis on a single or on a more restricted setup that will allow us to encourage work that is applicable to multiple settings. And I won't say a lot more, but the call is coming later this week. And you can find the details on our website, and details on the shared mission will be there later this week. So I want to thank, again, my collaborators on the works that I presented, Sarah Vigraf, Mark Marone, and Jacob Eisenstein, my advisor. The code is available on various repos, and thank you for listening.
Thanks a lot for the presentation, Yuval. We certainly enjoyed it. Does anyone in the live stream have questions? If not, I just wanted to ask you if you could elaborate more on the JSD and TVD trade-off. I think you had a slide over there, and
On this one,
can you please go to the slide that contains
the definitions. This one?
yes. Can
Okay.
you please? Yeah.
Yeah. So the two notions we're trying to quantify is how different the prediction is versus how different the attention distribution is. Okay, we have two models that make a prediction against an instance. Okay, it has the input that is a sequence of words, and then the output, which is a binary label. So, okay. So the output of a model is actually a score between -1 and 1, right? And then if it's positive, then we take that to mean positive, and if it's negative, we take that to mean negative, or between 0 and 1. And so the TVD measures the discrepancy between two models on the same instance. So this is like so on the x-axis here we have instances and the predictions made by two different models, and each makes slightly different predictions for each instance. But then together on the whole data set, we can sum this and use that as a metric for how different the model's predictions are. So in our adversarial setup, we want to minimize this because we want to create a second model that is as similar in its predictions to the first one. And the other hand, the JSD is that we want to do these, we want to maintain the same predictions while diverging their rationales. Okay, so we have, we want to see whether it's easy to make the exact same prediction while attending to completely different words in the same instance. Is that clear?
Yeah. Thanks for that. So I think what we can probably conclude is that the earlier paper said attention is not explanation. We can say attention is not always explanation.
Yeah.
Considering that you found in your experiments for certain data sets using a uniform weights baseline, yeah, didn't change the performance one bit. Um, do you have any intuitions as to why that happened for those models and for
Yes,
those particular? Yeah.
I have some very clear intuitions. So diabetes is a data set where if you look at the instances, you see that the positive instances would often include maybe a phrase or two that are very indicative and that basically mean this patient probably has diabetes, and then the prediction label would be positive. And those types of instances are hard to rationalize in any other way. Like as a human being, I would assume, or a clinical practitioner would say, like these two phrases are why I think from this clinical note that this patient is positive. Whereas if it's a negative example, then it usually just doesn't have anything, and you're going to have a much more uniform attention distribution in any case, and that is something that is also easier to diverge from. But since the data set is balanced, we have a lot of these positive instances, and they are hard to adversarially find a different explanation. Whereas sentiment tree bank is it's different in that if you have a negative or a positive review, then you're probably going to use a lot of words that are positive or negative. There's going to be maybe even some general tone that will be able to pick up on a specific word basis. Sometimes these have stylistic effects. So people who tend to write positive reviews use also different types of maybe even function word distributions, whereas that is not the case for diabetes, where doctors probably have the same style whether or not they're predicting or not predicting it.
Yeah. We have a question from the audience.
Yeah.
Amir asks, do you consider this, in quotes, explanation by design, in the sense that explanation is now not added as a post hoc consideration?
Are you referring to the future work part that I presented? The by construction part? This?
Let me clarify.
Because if so, then yes, that's the idea. So it might help to remember that the criticisms of attention as explanation stemmed from these facts in the first bullet here, that we take a model that was trained knowing all of the data, knowing all the instances, or all the parts of the instance, and then we try to attribute this to some mechanism, like the attention mechanism here, that is not really disconnected from everything else, right? It still has access via the hidden states or via other parts of the model to basically the entire input. So how can we be sure that if we try to make this explanation from the output of the attention module, that we are not just we're not just doing it because it's easy for us to claim that, or because it looks nice in our figures. And the first step I think we made towards alleviating that concern is the third experiment that we made, so the uncontextualized setting one. And then this one takes it one step further, when we actually remove the parts of the instance that we don't want the model to be able to see, so that it can think that it's it's just not using those parts at all this time. Like, we're sure that it's not using these parts.
Okay, thanks for clarifying that. So if we do not have any other questions, we can wrap this up. Thanks a lot, Yuval. It was a very interesting session, and I hope that some people in our ACE community are considering submitting to Black Box NLP. It's a very interesting workshop. If the audience is not aware of it, I think the talks of Black Box NLP 2019 are available online, so you can watch them. And
Okay.
yeah,
So thank you.
Thank you, and see you tomorrow, everyone. We'll be having a talk on visualizing and measuring the geometry of BERT. That's a paper from NeurIPS 29. See you, everyone, and thanks again, you all. Bye.
Thank you. Goodbye.